Hi everybody! In this lesson we will introduce the notion of a random variable, which is an object that assigns a value to each state of the world in the sample space. That value is typically a real number or a vector. In statistics, random variables are usually studied via certain associated functions, such as the cumulative distribution function, probability mass or density functions, and quantile functions. We will introduce each of these in this lesson. Let's first introduce the notion of a random variable. Recall that capital omega here denotes the sample space, i.e. the set of all possible states of the world or all possible outcomes, and that an element of omega is denoted by little omega over here. A random variable is then simply a function capital X which assigns to each member of the sample space omega a real number. In other words, it's a function that assigns a numeric value x of omega to each outcome little omega. Here's an example. We toss a fair coin 4 times. In that case, there are 16 possible outcomes, so the sample space has 16 elements ranging from heads, 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 tails, all the way down to tails, 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 tails. If the coin is fair, then each outcome is equally likely, and therefore the probability of any outcome is 1 over 16. Let us now define a random variable on this sample space. Let x be your winnings if you win 1 for every heads and you lose 1 for every tails. So x on the sample point HHHH is 4 because you've won 4 times. On the other hand, x on the sample point of HHHT, here you win 3 times, but you lose once, so your total winnings are 2, etc. Recall that events are subsets of the sample space. In other words, events are sets. The event that your winnings are equal to 2 is the set consisting of all the outcomes where you have 3 heads and 1 tails. In this particular case, there are 4 outcomes in this set, and so the probability that x is equal to 2 is 4 out of a total of 16 outcomes, and that is 0.25. Similarly, the probability that x is equal to 4 is 1 over 16. In statistics, the sample space omega often remains in the background and we study only random variables. What happens is the following. Tyche, the goddess of chance, picks a particular sample point omega from the sample space. This omega is the state of the world. Initially we do not know what it is, but it becomes apparent as we go along. We only see the value x of omega, which is a real number, of a random variable in that state. Cumulative distribution functions. Associated with any random variable x is its cumulative distribution function, or CDF, which is a function f sub capital X from the reals to the unit intervals, and it is defined as follows. F sub x of little x is simply the probability that capital X is less than or equal to little x. Here's an example. Consider the following game. A fair coin is tossed 3 times and x is the number of heads. Now the number of heads that you can get is either 0, 1, 2 or 3. So let's consider the graph of the CDF of x. Consider little x equal to minus 0.5 say, i.e. little x is over here. Well, the probability that you have less than minus 0.5 heads is 0. You can't get less than minus 0.5 heads. The smallest number of heads that you can get is 0 heads. So the CDF takes the value 0 over here. The probability is 0. Now let's consider, say, a number like 0.5. The probability that you have less than 0.5 heads is the probability that you have 0 heads. The probability of getting 0 heads means that you get tails, 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 and the probability of getting 3 tails in a row is 1 out of 8. And so the CDF takes the value 1 over 8 here. Consider now the probability of getting less than or equal to 1 heads. Well, if you have less than or equal to 1 heads, you have either 0 heads or 1 heads. We've already seen that the probability of getting 0 heads is 1 out of 8. The probability of getting 1 head, 1 out of 3, is 3/8. So this gap over here is 3/8, and hence its value here is 4/8, namely 1/8 plus 3/8. In the same way, the probability of getting less than or equal to, say, 2.5 heads is the probability of getting either 0, 1, or 2 heads. The probability of 0 heads is 1/8, the probability of getting 1 head is 3/8, the probability of getting 2 heads is also 3/8, and so now we are at 7/8 for the CDF. The probability of getting less than or equal to 3.5 heads is 1. You will certainly get less than or equal to 3.5 heads. Observe that over here on the y-axis we have probabilities. Also note that as we move to the left here, we go to 0, whereas if we move to the right, the value goes to 1. In addition, the CDF is an increasing function. It goes from 0 to 1. This is true for all cumulative distribution functions. Let's now consider some basic properties of cumulative distribution functions. We've already noted that the CDF of a random variable capital X is an increasing function, and that it approaches 0 as x goes to minus infinity, and that it approaches 1 as x goes to infinity. Recall that the values of the CDF are just probabilities, and therefore that they must lie between 0 and 1. It's actually quite easy to see that the CDF is an increasing function. Take, for example, x1 less than or equal to x2. The event that capital X is less than or equal to x1 is contained in the event that x is less than or equal to x2, because if capital X is less than x1, then it is also less than or equal to x2. Therefore, the probability of this event here is less than or equal to the probability of this event here. In other words, the probability that capital X is less than or equal to x1 is less than or equal to the probability that x is less than or equal to x2, and therefore the CDF evaluated at x1 is less than or equal to the CDF evaluated at x2 when x1 is less than or equal to x2. And this is just a definition of an increasing function. Furthermore, it can be shown that f sub x is right continuous. In other words, that the value of f at a point x is the limit of the values of f at point y, where y approaches x from above. Graphically, this means that whenever there is a jump in the CDF, then we have an open circle on the left of the jump and a closed circle on the right of the jump. In other words, the value of the function at the jump is equal to the limit as we come from the right. Also observe that if a is less than b, then the difference f of b minus f of a is just the probability that x is less than or equal to b minus the probability that x is less than or equal to a, and hence this difference is just the probability that x is less than or equal to b and x is not less than or equal to a, and thus it is the probability that capital X lies between a and b, where it is strictly greater than a and less than or equal to b. Now, it can be shown that two random variables have the same CDF if and only if they have the same distribution. In other words, that the CDF of x coincides with the CDF of y if and only if the probability that x belongs to b is the same as the probability that y belongs to b for any reasonable subset b of the real numbers. In that sense, the CDF of a random variable x completely determines its probabilistic behavior. In the example that we just considered, i.e. the number of heads in 3 coin tosses, the CDF turned out to be a step function. And this will always be the case for a random variable that has only finitely many values. In this case, the possible values were 0, 1, 2, and 3 heads, respectively. It is also possible for a random variable to take infinitely many values, in fact, any real value. And the most important example here is the standard normal distribution, which we will consider in detail later on. Its CDF is defined as follows, and the graph of this CDF is in this case a continuous function, without any jumps, in other words. Again, we can see that it is an increasing function which goes to 0 as x goes to minus infinity, and which goes to 1 as x goes to infinity. Let's now consider the notion of empirical distribution function. Suppose that we're given x1 up to xn, and that these are independent draws from a sample with distribution f. In other words, each of these values x1 up to xn is drawn from the distribution f. The empirical CDF f hat of this sample is then a non-parametric estimator of the true distribution function f, and it's defined as follows. Let's unpack what this means. Firstly, any estimator will be denoted by a hat, as shown over here. The subscript n means that it is an estimator drawn from n data points. We have here data points from x1 up to xn. This quantity over here is the so-called indicator, which indicates whether or not xi is less than or equal to x. Here xi is one of the random variables that we've drawn, and x is the number at which we evaluate the empirical distribution function. This indicator is equal to 1 if the value of xi is indeed less than or equal to x, and 0 otherwise. This sum over here, i.e. this sum here, therefore has a 1 every single time a data point xi is less than x, and a 0 otherwise, and hence this sum is equal to the number of elements in the sample that are less than or equal to x. So the probability that a randomly selected element from the sample is less than or equal to x is the number of elements in the sample that are less than or equal to x divided by the number of elements in the sample. In other words, it's the sum of indicators divided by n, and that is precisely the definition of the empirical distribution function. Note that the empirical CDF is a random function because it depends on the values of the random variables x1 up to xn. If you draw a different sample from the same distribution, you will get a different empirical CDF. The empirical CDF will typically approach the true CDF as the number of sample points, i.e. n, increases. Let's make this concrete with an example. Here we draw n is equal to 10 many random numbers from the standard normal distribution. The MATLAB command for this is as follows. In that case, x is a vector of 10 random numbers. If I repeat this command, I will get a different set of random numbers. Let's now plot these random numbers. Here they are shown on the x-axis. Take now the value x is equal to 0.5. The vector capital X less than or equal to 0.5 indicates whether a random number in that vector is less than or equal to 0.5 or not. And so that's going to be a vector of zeros and ones. The first random number was not less than or equal to 0.5. The second random number was less than or equal to 0.5. And we can verify this. This number here is not less than or equal to 0.5. This random number here is less than or equal to 0.5. In this case, the sum of these random numbers is 6. There are 6 random numbers that are less than 0.5, and so the empirical probability that x is less than or equal to 0.5 divides that by the number of sample points, and that will be given as 0.6 because there were 10 sample points. I could do this for any value whatsoever. For example, I could do it for x is equal to minus 1.3, and then the probability is 0.2. Or I could do it for x is equal to 4, and then the empirical probability is equal to 1, and that is because all of the points are less than or equal to 4. I repeat this now, not just for arbitrary values x, as I did over here, but for all the values of x values, in the range from minus 5 to 5. So for each of the x values in the range from minus 5 to 5, I compute this sum. and then I plot the empirical distribution function. As you can see, it has a jump of 1/10 at each of the sample points. If I make the number of points much larger, and I now plot the empirical CDF, I get something that looks very similar to the true cumulative distribution function of the standard normal distribution. In that sense, the empirical CDF approaches the true CDF as the number of sample points becomes larger and larger. Just to reiterate, here is the empirical CDF or ECDF of 15 draws from the standard normal distribution. You can see which numbers were drawn because there's a jump of size 1/15 at each of the random numbers. The true CDF is shown in blue.